Hello, differential equations. Today is March 24th, and we're going to talk right now about section 213. So this is the last part of our section 2.1, and it's about modeling epidemics using differential equations. So, I mean, when are we ever going to use this stuff? Pretty much useless. So let's go on. We're using the SIR model, not because it was knighted by the Queen of England, but because we're breaking the population down into three subpopulations: the susceptible individuals, the infected individuals, and the removed individuals. And we're only having this sort of motion right here: susceptible to infected to removed. And so I don't know if some of you have seen that little thing that Washington Post posted where they had like all little dots moving around, and some of them are infected and some of them are not. Well, what we're doing here is not going to be that complicated. Just that what we're doing here is that the change in susceptible is going to go down based on susceptible times infected times a constant. And so instead of doing something complicated, we're just doing the number of interactions also times probability of infection. We're not getting that complicated here. We're just keeping it simple. So we're just expecting that to be alpha times S times I. And so we're subtracting that from the susceptible and moving it into the infected. And then from the infected, there's a certain percentage of the infected who are being removed from the population every time. Again, that's really oversimplification of real life, but that's how we do math modeling. We do the simple one first, and then as we are going to learn some new mathematical techniques, we'll build on some extra ways that we can make it more and more realistic. So for instance, here's a graph of a possible situation. Alpha is 0.005, beta is 0.08. So some things we're going to continue to learn about in this class is, is there a period of time for which individuals are exposed to the disease but exhibit no symptoms and cannot infect others? Well, that adds a complication. Is the disease endemic? What is the prevalence of the infection? Can the disease be eradicated or controlled? What is the effect of the population age structure? So these are all questions we're going to explore later on in the class. But for right now, I just wanted to show you something that a friend of mine, who I went to college with, and he's now a professor at Hillsdale in Michigan, Dr. Mark Panaggio. He made this thing that's I posted to you on Moodle, and it is it's a Jupyter notebook, and he's using Dr. Panaggio does more applied mathematics, and so he's using kind of this model here, and he's made it so that you can use these sliders to change things. So for instance, what he's doing is the solid lines are the numbers if there's no social distancing, and the dotted lines are the numbers if there is social distancing. And so here, time is what time does the social distancing occur? Does it happen really early in the model, or does it happen really late in the model? You can see it happens really early. If we start social distancing really early, it can make a big change as far as how many people are infected and how flat that red curve is of infected. And again, so that's like not overwhelming the hospitals. Or if we start too late, then doesn't make any change at all, hardly at all. Now, then K is how much of a change social distancing. So this would be at 0, K is no change. So that's 0% change. And at 1, that would be 100% change. So you're seeing 100% less people. And so if you're seeing if everyone on average is seeing 73% less people, then that creates quite a big change. as long as you start early enough. Pretty cool stuff. So thank you to my friend Mark Panaggio for creating this. I invite all of you guys to find the link to this on Moodle and play with it a little bit. And we'll learn some more about this as the class goes on. And so if you have any, that's the end of this section. So if you have any questions, feel free to let me know.